Okay, this is a very cool one. We are going to see how to show that a multivariable function is differentiable everywhere. So of course, we have to know the definition of a function being differentiable. And this is very different than the calculus 1 definition. So let me write this down for you guys first. Definition. First, I'm just going to say this function, right, f of xy, I will call that z. So write z as f of xy. And we say f is differentiable at the point, that's the AB, if, here's the key, delta z, and right here, I'm going to use the phrase as follows. If delta z can be expressed as, and here's kind of like the formula. Here we go. Partial of f with respect to x at AB times delta x plus partial of y at AB times delta y. And now the rest is this very strange, right? Plus epsilon 1 times delta x plus epsilon 2 delta y. So we want to somehow work this out and then put it into this form. And moreover, we also have to do this. Once we have this expression, we also have to say, and epsilon 1, epsilon 2 goes to 0 as delta x approaching 0, likewise delta y approach 0. That is the definition. At first, you might be thinking, wow, that's so scary. But let me tell you, it's not. First thing first, this is what you want to show. That it has something to do with the calculus, the partial derivative, all that. But you do have to know that delta z. And remember, delta means the change. So this is how we define delta z. We have f of a plus delta x, comma, b plus delta y. And then we subtract f of a, b. And here's the idea. At the point AB, we can just plug in a into x and b into y, and we get the value for z. So that is the original value for z. But if you move a little bit in the x direction and a little bit in the y direction, we get a new value for z. So we do the new value minus the original value. That's how we really compute delta z. So this right here actually just requires algebra. And then hopefully we can match with this form with partial derivatives and also epsilon 1, epsilon 2. And hopefully epsilon 1, epsilon 2 will approach 0 as delta x approaches 0, likewise delta y approaches 0. So now let me show you if this works for this function. Here we go. First, let's write down PF for the proof. And then I will start off by saying, given any point AB, because we're trying to show that this function is differentiable everywhere. And then I'm going to let z be our function, which is 2x squared plus y cubed. And then we'll compute delta z first. By definition, this is equal to f of a plus delta x, comma, b plus delta y, and then minus f of ab. And then we just have to put this into x and this into y and do some algebra. Here we will have 2 times a plus delta x squared plus this into there, b plus delta y, third power, and then minus ab into x and y respectively. Put parentheses because we need to have two terms. So 2a squared plus b cubed. And then just expand this. So we have a squared times 2 plus 2 times this and that and then times 2. So it's 4a delta x. And then plus this thing squared times that. So it's 4 delta x squared. Put parentheses around the delta x. And then continue. When we expand the third power, remember the coefficients are 1, 3, 3, 1. Starting with the first term, cube that plus 3 times this square, and then this to the first power, and then plus another 3 times this to the first power, and then this to the second power. and lastly this to the third power. And then distribute the negative. Okay, and then we see that 2a squared minus 2a squared gone, likewise this and that gone. So that's just what we have for the algebra. Now, remember, we will have to put delta z into the form that we want, which is what? We want the partial with respect to x of a b times delta x plus partial with respect to y ab times delta y, and then we need to add epsilon 1 times delta x plus epsilon 2 delta y. So let's figure out what partial of f with respect to x and with respect to y are. So let me just write it down. Partial of f with respect to x, that will be just 4x. And then if we do it with respect to y, just this part, so it's 3y squared. Okay, have a look. I need to put ab into, well, just have x, right? So just a into x. So I want to have 4a times delta x, and that's exactly what we have right here. Super nice. So we will have this right here. 4a times delta x. And let me denote that this right here is exactly what we have for this. F sub x, ab. And then continue, we want this, which I just have to put b into the y, and 3b squared times delta y, which is just that. So we add 3b squared delta y, denote that this is f sub y, ab. So we took care of this and that. Now we want the rest. I want to have all the terms with delta x, which is this right here. Okay, that's that. So I'm going to break this down. I'll write this as plus delta x squared. I will purposely write it as 4 delta x and then another delta x. Because this way we can put this part as our epsilon 1. And then lastly, we have what? We have this and that. Both of them have delta y. I'm just going to factor that out. So we see that we have 3b times delta y and then plus delta y squared, and then we have that delta y right here. And this is our epsilon 2. And finally, we just have to make sure that epsilon 1 approaches 0, likewise epsilon 2 should also approach 0, under the condition that delta x approach 0 and delta y approach 0. Well, when I use this condition here, 4 times delta x will of course go to 0, so this right here checks. And when delta y approaches 0, well, this will approach 0, likewise that, so of course epsilon 2 will also approach 0. And therefore we're done. So just say thus, f is differentiable everywhere. That's it.